Hi everyone, hope you're doing good. I am thrilled to welcome each and every one of you to the IBM Z Event and Insiders 2 session. Today is a special day where I have invited PJ for taking the speaker role for this session. It's an honor to have such a diverse and enthusiastic group gathered here. So these events are more than just get-togethers, they're about sharing ideas and making connections. Join me in embracing new possibilities and making the most of our time together. PJ, I would like you to introduce yourself to the audience and tell us more about your journey to mainframes.
Sure. Thanks for having me, Rituraj. My name's PJ Catalano. I am the IBM Z and LinuxONE test architect. I've been with IBM for a little over 20 years now. I started my career with IBM as a co-op and intern during my senior year at college. I went to State University of New York, which is kind of right across the river from the plant in Poughkeepsie, New York. And I never left. I started doing, my first role was with some IO hardware testing. Then I went over to do some testing on the power subsystem components with the development teams. Eventually, I took a full-time position, testing third-party hardware with our IBM mainframe platforms. And about 7-8 years ago, I took over the role as a test architect. And my job is I am responsible for testing all the hardware and firmware components of the platform, Z and LinuxONE, before we release it to customers. So I take a lot of pride in what I do. My test organization is kind of the last defense of quality before we say it's ready to use, right? And if any customers hit problems or issues in the field using our platform, I take personal responsibility for that, right? Because that means it's something we missed, right, as a test organization. I'm also a master inventor. IBM has an inventorship program that's really exciting about awarding inventors. So as we come up with inventions and patents, whether they go in the platform or the general technology space, we accrue points, and then based on mentoring and give back, you get an honorary title of master inventor. And that's another kind of exciting aspect of my role. So that's me.
That's really amazing. Like, as per I know, there are not many, there are a lot of IBMers. Like, people say IBM is a huge company with so many divisions. We have IBMers in each and every aspect, whether we say AI, data, analytics, mainframes, power. But the thing is, not everyone can become a master inventor. So from my perspective, what I have learned is a master inventor is someone who is doing research and filing patents, and at the end of the day, there are not many people who are doing these kind of stuff, which leads to research and development in general in these companies. Yeah. So that's really nice and good to know about you. So you can just give your world famous virtual tour.
Okay. All right. Well, welcome. I'm going to share the screen. And we're going to go on a tour of our IBM Z and LinuxONE test facility. Let me PowerPoint. Wow. Okay, so let me just get a little organized, move things over around here. Okay, as I already mentioned, my name is PJ Catalano. I am the test architect for this facility. Now, this facility is based in Poughkeepsie, New York. As I said, we are right along the Hudson River, which is a big river that runs from the Atlantic Ocean all the way through New York up into Canada. It is a big river. And one of the advantages we have of our location is actually utilizing some of the natural cooling from the river to cool our data centers. Now, this is a 30-inch raised floor. If you're never seen a data center, generally, they are on a riser stack. This is 30 inches. The previous test facility we were in was only 18 inches. And the issue is during years and years of, I would say, bad hygiene, mainframes used to use IO cables that were giant bus and tab copper cables, right? They were literally this big around. They were so heavy that once they were installed, they actually were almost impossible to pull out of the floor, especially as these things stacked up. So previous tenants would cut you know, if there was a mainframe that was getting replaced or moved, they would cut the end of the cable, leave that big copper chunk under the floor, and then run new cables. Well, over time, that 18 inches where all the cooling happens actually started to decrease. And as you choke off that space under the floor, you get less and less cooling across your data center. And because of that, we actually had to rebuild this facility on the south end of the site to get there. So let's take a walk in. Now, I have some video here. It might be a little choppy, but this is kind of us entering the test floor. Now, if you were here in person, going inside, it is pretty loud. You're running at an average of 80 or 60 to 80 decibels, which, you know, is, if you're in here for a long time, you do need hearing protection. Now, my test facility has over 200 mainframes. Our job, as I mentioned, is to make sure the hardware and the firmware work before we say customers can use these platforms. Now, all the mainframes on this test floor are mine. They don't leave. These don't go to customers. There's another facility that builds customer units and ships them. These are all mine. Our main goal is to, again, ensure that as new hardware is developed, you know, Z16, the Telum processor developed, functionally those work correctly, and they meet all the performance characteristics that we developed for the platform. Now, if you're actually standing here in person, not only would it be allowed, but let me see, change my pointer here. Red. Yeah. Nope, sorry. Okay, so if you look down the hallway here, right, what you would actually notice is the lights in the ceiling would actually look like they're twinkling. And that's from scintillation. That's the process of heat rising, disturbing the air, and then the light hitting that wave, and you see the wavy patterns. You might see something like this if you're looking down a road on a hot day, right, in a trough. You might see, looks like the road looks like there's water on the road. But we have the same effect. This building, Building 12 in Poughkeepsie, is actually IBM's #1 power-consuming building in the world, worldwide. Our building, this building, there are, I think, there are 20-ish buildings in Poughkeepsie, New York, but this building alone actually consumes more power than the entire research center in Yorktown, New York. I'm proud of that, but also I get the target of a lot of cost-saving reductions and power-saving reductions. Now, I mentioned we're right next to the Hudson River. And what you're actually seeing here is on the left, there's these big black refrigerators. We call them crack units, computer room air conditioners. These units actually, how they work is they suck that hot air that's rising off the ceiling, suck it down into them. They chill the air and then blow that cold air down under the floor. Now the air spreads out, and you'll notice that, like on this tile structure here, maybe right behind my head, there's holes in that tile. The next tile, there's no holes. And the one after that, there's holes again, if you can see down there. So this is called hot cold aisle configuration in the data center. So as that cold air comes down and blows under the floor, it's going to come up on certain aisles, the cold aisles. The cold air comes in, gets sucked into the systems, and then the hot air blows out on the other side. Now, we alternate the systems because we don't want the hot exhaust blowing into the intake of the next row. We actually want hot blowing on hot so that air rises up. And that's what we use to kind of have a convection loop in the data center. Now, where the Hudson River comes in is this is water chilled, right? So there's water piped in here. We actually pipe the water that exchanges here out to the Hudson River to chill it and bring it back. So it's not like we're sucking water in from the Hudson River, but we are using as a heat exchange loop. Okay, let's take a walk over to the side. So this is, we're going to walk over and take a look at one of the smallest systems we have on the floor. As you're passing by, you'll see there's lots of cables, lots of different generations of systems. We'll talk about the multiple generations we have in a minute. But this is where one of our more unique systems live. And this guy right here, his name is Beamer. He's called Beamer because we actually send this guy to a medical university. We put him in a van. and then we put them in a radiation cannon that's used to treat cancer patients. So this Z system actually has to sit in a table or on a chair where you would put a human being. What you're looking at is, again, the smallest footprint. On the left here is the KEC drawer, the compute drawer. We'll take a close-up look at that in a little bit. Next to it is the I/O cage, and on top is the support element. It's a 1U rack mount server that basically controls the firmware and the configuration of the hardware, and he's run over here from the side. Now, the reason we're firing it with a radiation cannon is computer electronics are susceptible to cosmic radiation. What that means is if cosmic radiation comes in and hits electronic components, depending on what it's hitting, it has the potential to cause bit flips, turn a 0 to a 1 or a 1 to a 0. Now, the chances of that happening on Earth are fairly rare. But in order to ensure our hardware will hold up to those fairly rare occasions, we need a way to speed up that test process. And we speed it up by firing gamma radiation at every single hardware component in the system and validating we can detect when those bit flips occur. If we can't detect when those bit flips occur, we actually have to throw out the design and start over again. And we've done this multiple times. Certain components like FPGAs, field programmable gate arrays, right, which are rows and rows of different logic switches that you can change the logic on. Those are very susceptible to cosmic radiation incidents. So we've had designs that included FPGAs that we actually had to say, this doesn't work. It is not hardened enough. We actually have to replace it with a real ASIC or real hardware. So this test is very valuable to us. Now let's spin over and take a little look into the drawer itself. If you have any questions, feel free to speak up and stop me. Otherwise, I will just keep talking. So this is the KEC drawer. So like our mainframes, generally people think of them as a computer, which they are, right? But it's a little different than the PC or laptop you have. The mainframe itself is really just the processor and memory with I/O. Your hard drive, your storage actually lives outside the box. And we're going to go look at that. We usually call it a disk array or DASD for short. But that's where the storage lives. What you're looking at here is a drawer that actually holds the CPU and memory in a Z16. Now, the way this is configured is you have, well, let me start here. So on the left here, this is a DCM, a dual chip module. This DCM contains 2 Telum processors. Okay, Telum processor is the brand new processor design, has AI integration into the chip, so you could do at transaction time inferencing. But in each of these DCMs are 2 Telum processors. And in every drawer you could buy or get, you have 4 DCMs plugged in that drawer. You could have up to 4 drawers in one system. Okay. Now, on the left is the memory. So this is all the RAM, if you will, right? These memory modules plug in. We can support up to 10 terabytes of main memory per drawer. 4-drawer system, you could have up to 40 terabytes of RAM. Now, the Z16 comes in multiple models, but there's 2 different versions. There's a high-end version and an air-cooled version. This is a high-end version drawer, and you can tell that because it has these tubes here. In the high-end version drawer, we actually have a closed water loop that runs and cools the processors, and then runs to a radiator at the bottom of the rack. Again, we'll look at a radiator a little later. If this was a air-cooled system, you wouldn't have these loops. And instead, you can see up here above my head, this is a giant heatsink. On each of these, you would have a giant heatsink. Now, there's always air blowing front to back on this drawer, even on the water-cooled system. But the reason we could actually go to the heatsink is those chips run at a little lower frequency, so they consume less power, generate less heat, and the air cooling could stay, keep it cool for operational purposes. That's the KEC drawer. So let's spin around. Another neat thing we do is we use these thermal chambers. I have 4 thermal chambers on the floor. You're looking at 2 of them. There's another set behind those. And what these are is you can think of them as big refrigerators and ovens. We get a system, we roll it in there, we plug all the I/O and all the processors, we close the doors, we start workload, and then we swing the ambient temperature from 4 degrees Celsius up to 40 degrees Celsius. That's actually the operational envelope of our systems. It's one of the most strict operational envelopes. There's an ASHRAE standard that qualifies operational range, and that's the biggest envelope. Now, the reason we do this is a couple. One is as sustainability, energy conservation is becoming a higher priority, especially around the world as also costs are increasing for energy. We have a lot of data center operators asking us, instead of running the cooling at 24 degrees Celsius, can I run it at 27 degrees Celsius or 32 degrees Celsius? So by not cooling the data center as much, right, they want to save costs, and our machines can operate in those envelopes. So that's one reason. The second reason is we want to be able to sell these things worldwide to any temperature, any altitude, right? And within that operation envelope, there's also altitude range restrictions. So this thing could run at, excuse me, like 3,000 meters above sea level, some crazy number, at an optimal cooling temperature, right? So we could kind of sell these things to places, and people are looking for more and more unique places to place data centers where they could get a cost advantage from some of the things like geothermal or river cooling, right? So we're getting stranger and stranger requests as to where they want to put them. So we want to make sure, as part of the design and part of the test, we can function in any, enclosed environment. All right, we're going to swing around. Now we're going to start talking a little bit about the I/O. So I mentioned, the basic components of Z16 are the KEC drawer, where the compute happens, the processor drawer, and the I/O drawer. And as I mentioned previously, right, that the hard drives themselves don't live on the system. So I/O is very important to us because we need to access the storage. And in storage is where things like all the databases live, bank accounts, insurance records, right? All the things are mainframe touch. And what we're actually looking at here, this is a pretty cool piece of technology. This is called a wavelength division multiplexer, WDM system. And so IBM doesn't make this. We have a couple third-party vendors that make these. And as I mentioned in my first role, full-time role, I was kind of testing these, interacting with Z systems. So what you're looking at and how this works is, for resiliency purposes, right, a lot of the mainframe clients, customers are in highly regulated industries where there's a requirement that they have more than one data center that are far apart. So that way, if there's a power loss or some natural disaster that takes out one of those data centers, the other one could take over. Now, why are these industries regulated? Well, these are some of the world's most important industries, as I mentioned: banking, finance, travel, right, insurance, medical. You can't afford to take the outage because that will impact real people in their lives. But in order to have multiple data centers, you need to have connectivity long distances, right? Because if I lose a storage in one data center, I still need to access it from the other data center and vice versa. So this technology allows you to transport hundreds of channels over a very single pair of fiber. So let me explain what you're looking at. So these yellow cables are our fiber optic cables, and we'll look a little bit more at the yellow cables in a bit, but all the wavelength, all the color of light on those cables are exactly the same. It's 1310 nanometers. So let's just say they're the same color. We'll call it colorless for this discussion. Those colorless lights in each of these cards that they're plugged into, this system actually converts that light to a different color. And each color on those cards is a unique color. It's different from every other card. Because light's non-destructive, I could actually take all those colors of lights, put them through a prism, and then focus them into a single piece of glass. And that's what you're actually seeing coming up here. So this is a single strand of fiber optic that has 160 different colors running on it. This box on the top is 50 kilometers of fiber in that box. Not simulated. It is real 50, a spool that's 50 kilometers long of glass in that box. In the rack next to it, there's another 50-kilometer box of fiber. So this rack on this side is actually physically 100 kilometers away from that rack right next to it. Once that light goes that 100 kilometers, gets to the other box, we put those 160 colors back through a prism, split them out to each of those cards, convert it back to the colorless lights. And that allows customers to run hundreds of channels, right? Hundreds of kilometers without having to have, massive and massive amounts of cable. So this technology is very important to how disaster recovery and data center resiliency works for our platforms. We're going to swing around to the other side, and we're going to look at some of our storage. So these are the mainframe hard drives. What we're actually looking at here are DS8000. So this is IBM's enterprise class storage product that we make. On the left, left that way, DS8900 is the latest generation of storage. The 8800 is the generation before that. When we went to the 8900, you could see the F. The F stands for flash, all flash. There's no more spinning disks. In the 8800, about 75% of the drives were actually spinning disk drives. The other 25% were solid state or flash. But now it's all flash, no spinning disk. I have about 100 of these control units across my floor. The reason I have so many, they have multiple functions. One, from a hardware test point of view, these are just really big targets that I'm trying to drive as much I/O to. I don't care what the data is or if the data is preserved for a long time. I just want to write as much as I can and then read it back and make sure what I wrote and what I read at that time match up. For a software test point of view, this is where all the operating systems live, all their data sets, all the databases, right? So they live on the hard drives. They IPL, initial program load, the operating system. It's basically booting the operating system onto the mainframe from these devices. And then they look at from the I/O attached to do their reads and writes and keep their data sets consistent. The other thing we use these for, as I mentioned, the disaster recovery. So like these are two separate control units. Well, this control unit is 100 kilometers away from that control unit. How? Using that DWDM that you can see back here. So this disk is actively mirroring to that disk. Just means it's copying. It's a synchronous copy. Every time I do a transaction to this disk, I say I do a write. This disk doesn't respond back to the mainframe until that write is written to his local disk. It's written to this disk. This guy acknowledges it, and then he sends that acknowledgement back to the mainframe. So that's synchronous disk replication. There is also asynchronous disk replication where it writes and then over time they'll copy. But again, there's different application performance implications to the two different styles. But what we're trying to do from the Z side is we're driving I/O heavy to this guy. He's doing the mirror. What we also want to do is as we're driving I/O, basically rip one of these guys away, take him away, pretend he failed, and make sure all my data was copied and read from the other side. So those are some of the disaster recovery scenarios that we do on our floor. Again, to make sure that if a customer does have a real event where they lose a control unit, lose a data center, we've tested those scenarios without having data centers 100 kilometers away. We could do that all in-house, a couple feet away from each other, and basically have that same, the latency of a real separated data center. So we're going to swing around back here. The majority of these cables you see, these yellow cables, are one of two protocols. They're either FICON or fiber channel. Those are really the two storage protocols that we use on a mainframe. FICON more so than fiber channel. FICON is actually a special flavor of fiber channel. There's some more requirements on top of the fiber channel standard. But But what you're looking at here is fiber channel and FICON switches. If you're familiar with an Ethernet switch, it's the same concept, right? Is I have multiple devices going into a box that I want to talk to multiple other devices. So I need a switch that does all the routing for me. And that's what you're seeing here. There's really two vendors that only make these in this space, Cisco and Broadcom. You could tell the vendors differently because of the way the blades sit. So sideways blades like this guy on the left, that's a Cisco switch. Behind my head, you see up and down blades. Those are a Broadcom switch. But they both serve the same function, right? Is I have my fiber channel coming in, and that'll allow me one link to come in from a Z to talk to multiple DS8000s without having to drive individual links to them. Or again, if I'm on DS8K, I could have multiple Zs talking to that single DS8K over a single port. Obviously, for redundancy, we want to do more than one port, but this enables kind of the majority of connectivity across our floor and allows us to share. That way, I don't need to have dedicated storage for every mainframe. And we do a lot of sharing. We are a test environment, right? We want to make sure that our sharing is probably higher than what a customer would use, because that's what we're always trying to do. We're always trying to push the edge beyond what we think our customer would be running at, to make sure things hold up. So that way we hope they don't hit that threshold, but if they do, we can ensure it's still good and working. Now I'm going to spin around here and walk into this room. Now, this is my patch panel room. I have over 200,000 fiber optic connections in here, 200,000. The reason I have so many connections is all the devices that sit out around the rest of the test floor, they don't actually connect to each other directly. They all come to this room first. So that switch, all those cables come to this room. The storage come to this room. Every Z comes to this room. And then I do the connectivity between those devices in here. You say that's crazy. Well, we are a test environment and we do a lot of crazy things. But one of the things we're doing is we're rapidly reconfiguring, what our sister environments look like. We're also moving things in and out of test cells more so than a normal customer would. So this gives me the flexibility to rapidly change configurations without having to run cables hundreds and hundreds of meters under the floor, then pull them out and move them over and figure out, right? So this patch panel room, it really allows us that flexibility. I have 4 people's full-time job just to live in this room. And that includes making sure the fibers are clean, because even though they're plugged, dust still gets in there and dust settles. So we have to continuously clean these things. And second is to make sure that every fiber connection is well documented. So that way, when we have to do a reconfiguration or change, we're not guessing where we have to go. So that's what this main room here is for. Now, you'll see there's really like 3 different color fibers. We talked about the yellow. There's also orange. You'll see there's like a little orange trunk here. There's some orange on the top. And then there's like this light blue teal color. Let me explain the differences. The yellow cable is what we call single mode cable. It runs at, the optics run at 1310 nanometers. That's the wavelength of light traveling through that optic. And the core, the glass in the middle that the light travels through, is 9 microns thick. And it's about the thickness of a human hair. The orange is multi-mode. That is 85 nanometer wavelength. And the core is 5 times as thick. It's actually about 50 to 60 microns thick. Fiber optics, actually, the cables actually have a bandwidth associated with it. It's not very intuitive unless you study some optical theory. But the thickness of the cable, the less light you allow in there to actually enter the core, the further you could allow that light to travel. And the reason is, if you think of a pulse like a 1 to a 0 transition, well, if that is fiber optic, it's not a square pulse. It's kind of the ramping up, right? So it's a little bit of a sine wave. But because you're getting more rays of light, more modes of light into the fiber, you're going to get like multiple pulses, right, that represent a bit. And then as they travel, the pulses will spread out and shrink. So the transmission length will decrease on a multi-mode. Every time I double the speed on a multi-mode cable, so if I go from 16 gigabit per second fiber channel to 32 gigabit per second, I can only go half the distance. Because I don't want to reconfigure my data center, and a lot of clients don't want to reconfigure their data center every time they increase the I/O speed, kind of every other generation or so, by basically bringing all the devices half as close, they invest in the single mode fiber, the yellow. It is more expensive, but there's basically a guarantee that we will keep 10-kilometer range every time we continue to double the speed. That'll never half. So that's why about 99% of my cables are those yellow cables, so I don't have to reconfigure my data center. The blue cables are unique here. Those are also a form of multi-mode cables, and there's two use cases for that in Z. The first use case is PCIe coupling, so short-range coupling. If I have two Zs and I want them to talk together in a sysplex, which is a fancy way of saying, where they coordinate their workload together, kind of operate as one big environment. Short range coupling travels that. It's just PCIe extension over the multi-mode fiber. The other use case is for a special link called Z Hyperlink. That is a direct I/O link from the processor on the Z to a DS8K cache. So that allows me to do, it reduces basically the I/O latency from the processor to the DS8K by a factor of it's 1/10 the latency. So a traditional I/O operation would take something like 150 microseconds. This will take sub 10 microseconds to happen. The limitation on that cable is 150 meters. So you really need to think about like, what's the use case for this, right? There's some very good use cases around ZOS and ZOS DB2 log transaction or log records. But more and more people are trying to figure out how to use that. Right? Again, you need to design your data center to have your storage 150 meters within the processor itself. But there are use cases for it, and that's really what we use those two cables for. Okay. Any questions? I'm going to take a break. Any questions? I see a hand raised. Good, Eugene.
Yes, PJ. I'm not sure if I got you. I think I missed the point somewhere. Why are the icons 10 kilometers long when the mainframes are next to each other?
Great question. So the optics are so that 10 kilometer is the rating on the optic, the fiber optic we use. So I don't have a good picture of an I/O card coming up. So in our I/O cards, we have multiple ports. Each of those ports, we have what's called a SFP, small form factor pluggable optic. Those we get from a third party, but the rating on those for the long wave, right? Those yellow cables are generally 10 kilometers out of the box. That means that optic can go natively 10 kilometers of fiber. Now, you say, well, most data centers are close. That's true, but we also have use cases where if I have a campus, right, and I have multiple buildings and I want to go building to building, right, DWDM is a little bit of expensive cost, right? So if you're going hundreds of kilometers, DWDM makes sense. If I'm going from, here to 3 buildings away, I could do that, within that 10 kilometer range, right? So why they pick 10 kilometers, I don't know, but that has been an industry standard since 1 gigabit optics on the fiber channel side. But that's just really a statement of how powerful the laser is in that optic, right? How much optical transport power you have. And if you go into study fiber optics, right, the way we measure how much power you need is called a link budget. Basically, your link budget tells you how much loss you're going to have between each fiber, each patch panel. So the 10 kilometers is great if you're going straight out, but every time I go into a patch panel, I lose about half a dB of light. If I go through multiple patch panels, right? So the distance statement is a little bit of a misnomer in the industry. It's the way it's been, but basically it's telling you how much power it has. And then you could kind of convert of like, well, it's really not 10 kilometers if I go through 3 patch panels. It's maybe only 8 kilometers, right? But if I have to go 3 buildings, I might have to go through 6 hops, right? 6 of these patch panels, because every building has a patch panel and I got to go through the, right? So that's how kind of that 10 kilometers gets eaten up, because it's really just a power statement, not a real distance statement. Hopefully that answers.
Yes, it does. Thank you. It makes sense.
Okay. Nambali has a question?
Yes, I do. Thank you for the tour. It was very fascinating. So my question, I have had an experience with a server, right? I've been able to open one up and then see the components, switch one on. It made a lot of noise. So, okay, my question is, what is the difference between a mainframe and a server? Is a mainframe a type of server, or is there like a distinct difference between the two?
So short answer is they're both computers. Mainframe, the architecture is significantly different than like a x86 Intel platform, right? And maybe this, now that we see here's actually a row of multiple mainframes together, right? So when I say mainframes are real big generic term. Let me get a little bit more specific, right? So the latest platform from IBM is Z16, IBM Z16. And then there's the LinuxONE Emperor 4. We're going to see a LinuxONE, I think, in a second here. But it's basically the architectures are different. That's the short answer. Mainframes are designed for high resiliency, high transactional processing. That's not what like an x86 architecture is designed for. So over time, those architectures started similar, but they diverged because we were solving 2 different use cases. So, mainframe can run Linux, just like any other server could run Linux, and we could run basically all the major versions of Linux: Ubuntu, Red Hat, SLES, right? So if you're a Linux operator, right, and if you know Linux, you could run Linux here. Same, right? The things that there's more benefit here is actually our architecture allows for multiple cores to work together. So you get better and better benefits of consolidation on a mainframe versus just adding another rack of a 1U rack server. We also have advantages on the I/O consolidation. So on a single mainframe, I could have up to 300 ports of I/O. And I could share a lot of those ports. So that way, if I lose a port, I still have access to whatever we're getting to, right? So a single use server might have like 2 fiber channel ports, 2 Ethernet ports. I have hundreds, right? So if that rack, if somebody bangs the rack and knocks those 2 cables out, you've lost access to the rack. Somebody bangs and knocks 2 cables out on my mainframe, I got 100 others, right, that I could get access to. So the design point for the mainframe technology is around resiliency, availability, and serviceability. The other thing that's cool about mainframe is I can replace every single component in this guy without shutting the thing off and while workload keeps running. As long as you have 2 of those things, which generally every system has 2 of, I can replace that one thing that's broken without taking the system off. Your workload keeps running. No other system in the world does that. And our architecture needs to support the mobility of that workload to achieve that. So that's kind of the big differences of the mainframe. There are some more subtle differences, around Indianness. I don't know if you're familiar with the concept of Indianness, of the order in which high-level bits or low-level bits are stored. I don't want to get to, there are technical differences, but if you're a Linux operator, it just runs Linux, right? But we also run our special operating systems like ZOS, TPF, Transactional Processing Facility, ZVM, right, are all kind of architected to utilize the uniqueness of our platform. The other thing that's cool about IBM is we're a full stack development company. We make the chips, we make the architecture, we make the hardware, we make the firmware, we make the middleware, we make the software. So we actually build value all the way through. So if there's some ZOS operation, right, that we want or need to run faster, we could design a special instruction in the processor that'll run that operation faster. And there's no other company in the world except maybe one, Apple, that actually does all the hardware, software, and integration, right? Apple's doing it for iPhones and MacBooks, right? But we're doing it for enterprise class storage. Great question. So we're still going. I was just taking a break for questions. So we're not done yet. So what we're looking at here is, this is a little bit of a family photo. So we have multiple generations we support. Usually we support 3 to 4 generations in the field of systems. And what we're looking at here is all those generations that are currently supported. On the right, this is the latest and greatest Z16. It's in a 19-inch rack. And next to it is a high-end Z14. What I want to show you here is Z14, this guy over here, he's actually these two frames together. This is one system, was the last system we shipped in a 24-inch rack. So the rack from here to here measures 24 inches. Z15 and Z16 all shipped in a 19-inch rack. 19-inch rack is the industry standard. Our 24-inch rack put us in a little bit of a unique position. If we went in, as you know, we were doing consolidation plays I was talking about with Linux and saying, hey, you could replace 2,000 Linux servers with one, LinuxONE system. And they said, that's great. But by the way, since our system's depth and width is different, you have to go stick it in another part of your data center. That was not a conversation customers want to have, right? If I'm going to do a replacement, it needs to go in a similar spot that it went to. So that forced us to kind of rethink our design and get to an industry standard 19-inch rack. So Z14, next to it, this is a Z15, and then all the way on the end, this is another Z14, all the way on the end, the last two is a Z13. So this is kind of the family photo of all the currently supported generations in the field. Let's swing around. We're going to look at a fully configured mainframe next. So this will really show you the scope and scale of what makes mainframe unique, is because of the mention. It's the resiliency, the availability of the system. So this guy up here, this is A40. He is a 4-frame system. So starting on the end, 1, 2, 3, 4. So up until this point here, this is all one system. It's I gotta go this way. I'm nervous. All one system, managed as one unit. This is a max configured system. What does that mean? This is a 4-drawer system. We call this a max 200. So when we sell these systems, we sell it basically by the cores and the I/O. So max 200 means there's 200 customer usable cores in this system. That's the highest you can get, okay? 4 drawers. Now, just because there's customer usable cores, there's actually more cores in that system. We have things like sparing. We have lots of, again, redundancy built in. So if you're running and for some reason a core fails, we have extra cores we just turn on. You'll never know. We have cores that do some specialty work for us that are kind of customer usable. But 200 cores. So that's 4 KEK drawers. There's actually, the cables are a mess, but there's 3 KEK drawers in this guy, and then a single KEK drawer on this side, and 11 I/O cages. So here's 3 I/O cages. There's another 3, another 2, another 3, and then, sorry, there's 5 in that guy. I think that adds up to 11. But 11 I/O cages is the max that you have. So what's really unique here, this is like we're looking at that full system. Up here, up top, there is a cylinder that's behind that black cage. That's the reservoir. We actually put water in that, and that's what runs through those pipes we saw in the KEK drawer. It's a closed water loop. And then on the bottom, you can see there's some hose connections. There's like a connector here, connector here. That's the radiator. So that cold water loop comes through the processors, goes through the radiator, and there's a fan blowing across that radiator to chill that water, to cool it back off before we pump it back up. Closed loop, that water never leaves the system. In this I/O cage here, there's lots of, basically all the I/O connections you can think of. Ficon, fiber channel, coupling. We mentioned Sysplex earlier. Coupling channels are the way the Sysplex talk to each other and coordinate with each other. We have different Rocky and Ethernet connections as well that allow us to do kind of transactions on and off the platform. Did I miss anything else? Any other I/O types? I think that's all of them. So you can see how the system actually works. So up top on this guy is those support elements, those 1U servers that connect to this keyboard and monitor. This is a support element. Generally, these are only used like when somebody's at the system servicing it, like replacing a part, repairing a part. Generally, multiple support elements can be managed by what we call an HMC, a hardware management console. That's kind of remotely accessible, and that's generally where most of the customers do the work. Because I'm a tester, I do a lot of my work directly from the SE, but customers will manage their work at a much higher level than we do on the test floor. The other thing I got to ask is, like, what is this brick here? Well, this is actually a fire retardant material. So I'm 30 inches off the ground. All my cables actually go down the floor and then route out. Well, in order to reduce any chance of, if a fire were to happen, we don't want fire to actually get air in and crawl up spaces. So this hole here, that brick, we would jam it in that hole to make sure that there's no airflow. One, it's fire retardant, and two, it actually prevents cooling loss, right? Because this is actually the hot side of the aisle. We don't want cold air coming out of here. So that blocks also the cold air coming out. You can see on the other side, it has those perforated tiles where the cool air comes out and comes in this way. Let's spin around to the front. So this is actually what the system looks like with covers on. Now, most of my systems don't have covers. I am a test shop. We're doing a lot of reconfiguring. But this is what that system would look like with the covers on it. These are some pretty cool covers, really nice industrial design. They won a Red Dot Design Award earlier this year it's a highly prestigious industrial design award, and they just look pretty cool. We got a couple more stops coming, but one question I often get asked is, well, how do you get the mainframes onto the 30-inch raised floor? Well, here's your answer. What you're looking at in the back here this is like a loading dock door that would open and close. Just beyond that is actually a real loading dock where trucks would come and drop the mainframes off for us. So manufacturing builds them or ships us the parts. We then push the system up onto the floor. There's a ramp here for a smaller system. There's a lift here that gets the systems. But that 4-frame system that we saw, how it's actually shipped to us and to customers is each rack is individually shipped. All the components are already in it. We ship that system. We would roll each of those individual frames to the floor and then bolt them together. And then interleave, there's some cables that go between racks, bolt them together, interleave the cables between the racks, and then turn it over to a customer. Now, one of the new innovations for Z16, this year we released the rack mount system, Z16 rack mount. As I mentioned, traditional high-end system and even the air-cooled system, when you would buy it from IBM, we would ship you the rack with all the components in it. And all they would have to do is basically roll it into spot. If there's multiple racks, connect them up, and then put power to it. And then that was it. Turn it over to the customer. This is a traditional air-cooled on the side. On the right is a rack mount. Now, the difference is the rack mount is the customer provides the rack, customer provides the power supply. We ship those components individually, and then an IBM installer actually will place the components in the rack for the customer. The reason we had to do this is the rack next to it, that way, you can see in this spot here, there's actually no component. We actually have to put a filler plate. The way we safety test these things, we're not allowed to put other vendor hardware in there. But as consolidation began to become important and things like colo data centers where your hardware sits in somebody else's data center and I'm paying by the square foot, well, they want to minimize, maximize the density, minimize the footprint. This configuration, the rack mount, it's your rack, your power supply. You plug our stuff in. In this empty space up top, you could put any third-party hardware you want. You could put a storage box, you could put a SAN switch, you could put an Ethernet switch, you could put a power server, you could put an x86 switch in there, right? It's a kind of new way to kind of consume and build Z that we've never had before. So the only different components on these two platforms themselves actually are the covers. And this is a terrible shot, but down here on the bottom, there's actually a cover that goes on each of these components here. When we do the traditional high-end and air-cooled, we ship them with those doors I showed you earlier. Those doors actually have an embedded filter. So when that cold air comes up and the fans suck it in, there's a filter so that if there's any type of particulates in the air, we don't suck that into the system. Well, in the rack mount, we actually don't know if the rack we're going into has a door. So we still want to protect our system. So we design new covers for the individual units that actually have built-in filters in them. That's the only difference between the rack mount and the high end when it comes to hardware, which I thought is pretty neat. Okay, we got one more stop on the test floor tour here. Any other questions while we're walking?
How much does it cost?
Oh, go ahead, Eugene. Sorry, I talked over you.
How much does the mainframe cost?
I can tell you the list price. So here's the business. If you ask, so I'm not a sales guy. Let me caveat that. Do not quote this as real numbers. The entry-level mainframe, you're talking about $150,000. A40 that I showed you, fully configured, you're talking upwards of $20 million. Okay. Now, let me caveat it in saying nobody pays the list price. Right? There's always deals going on. These things are often sold with software bundles, service packages that adjust the price of the hardware, right? Based on the software consumption model. So the price varies is the short answer. Long answer is you could get in for a low cost of $100,000. They are expensive systems. It's really custom hardware designed, and they're purpose built to do what they do. Last stop. So this is actually the first stop that the hardware comes once we get new hardware on the floor. So this is our bring up system. So when we get new chips, like when we design the Telum processor from start, right? We only build a handful. It's really, really expensive to make changes once you start manufacturing chips. So the first set, we really only build a handful. And what we want to do is validate that our logic's working. Things like signal integrity are good on the chip itself. And they come into this system. And what you're actually seeing here is you'll see there's a rack here. And then next to it, there's this funky little cage. Well, in this configuration, those compute drawers, the Keck drawers, are actually in that cage. So those new chips come in, go into the Keck drawers here. The reason it's in that cage is we actually want to measure voltage levels, signal strength. And in order to get to those components that are in those drawers, we need to do something a little unique. This guy next to it is actually the same configuration, but that rack where those Keck drawers is rotated. So if you pull this pin out behind my head, that thing actually will spin and swivel. And that gives us access to those chips on the bottom, the motherboard. So these are special motherboards that will allow us to probe through that connector, the socket that chip's on, so we can do cool little measurements that normally we wouldn't have been able to get access to just based on the location of the hardware in the system. So this is a nice little like electrical engineering, mechanical engineering crossover we have on the floor. But these where that early validation of those chips come in, and we say, is the design good before we start printing hundreds and thousands of the chips after the fact. So that's my tour. We're actually just going to walk out here through my operator center. So this is we call it the quad. This is actually where the majority of my testers sit and run the system, because it is loud out there. So this room is insulated from sound and gives us, actual place to work and sit. This is actually where I sit every day over here in this corner and kind of run and manage the team from the test floor. But this is the lab tour. stop here. Any questions? I have to get my head size right. Yeah, go ahead, just ask.
So I would like to ask, this would be quite important for most of us. What will be your advice to someone who is in their 20s, going to college, learning about computer science? So how to build an amazing career in any field?
Yeah, I mean, you have to like what you do. Let me start there, right? You need to have a passion for the either technology or the coding, right? You have to start with something you like. If you don't enjoy what you do, you're not going to have a fulfilling career, right? For me, early on, I knew I wanted to work with computers, right? I love video games. I love building computers to play video games. That started me on the path of engineering, and coding, and I enjoy it, right? And I get paid to break things, which I think is a pretty cool job. So having a successful career starts with knowing what you're good at and what you enjoy. If you could find that thing that crosses over both, even better. From there, right, my career advice always is get in, right? It might not be where you want to start, but if there's a company you like or technology you like, get in. Whatever it takes, get into it, right? From there, right, the avenues then expand. I could really only talk about IBM because it's the only company I've been with. But IBM is a big company. Getting in is the hardest part. Once you're in, there's a million things you could end up doing, and you can kind of go pursue those things. If you know what you want to do and what you like doing, then getting in is kind of the key step one. The often question I get is, well, how do you get in? Well, there's lots of programs and apprenticeships. Yes, in the mainframe industry, it's kind of hard. I think LinkedIn is probably one of the best places to be right now if you're looking to get into the industry, connect with people in the industry. I try to share all the jobs I see when other companies post mainframe jobs, find people in the community, interact and engage with the community, with the student ambassadors, with the champions, right? That's really the pathway into this career here. I'm actually let me stop sharing, that way you can see my face bigger. But that's my advice of kind of having a career. And then again, it's finding the passions that you like and sticking. Oops, sorry. Let me move you guys over here so you don't see the side of my head. Finding things that keep you interested, right, and keep evolving, right? For me, social media in the last year or two is really a reinvigorator of my career, right? I started doing it out of brute force, right, for hoping it would help get me career growth. I ended up falling in love with it, and I really enjoy doing that. And that's kind of turned into a possible new career path for me, right? And it's just, again, finding things you like and keeping it interested for yourself. Nobody else is going to do that for you except you.
That's amazing. Like, even I would like to add one thing here. Most of us have seen that there are people who are making cringe content on Instagram and all these platforms, LinkedIn, creating memes. So why not us as an engineer create tech content? And even these kind of contents are really appreciated by people who are in tech. And like you must have seen reels on data science careers, the roadmaps, and how to build a career, these kind of videos. So it's always about, if you're interested in doing something, each one of us have some story to share. If I am in my university, I am doing something, let me share that. You may think like I'm not getting likes or I may not get followed, but that's totally fine, because it's just counts in small and small efforts you are bringing into the table. People are noticing you, and eventually you get the opportunity at the right moment. So it takes time. Obviously, it took me more than an year to become a champion. Just after me starting advocacy, as soon as I became the ambassador in January 2022. So by 2023, the whole year counts to be a champion. So I always recommend people who want to be an IBM champion, you can be an IBM champion if you have that whole 12 months of advocacy, and you don't have to do a lot of it. Just 2 to 3 contributions every month is fine. You don't have to spend whole month just figuring out what to post. And I do it excessively, so that's another thing, but still it works.
Yeah, I had it, and I said when I forced myself to start, let me be a little bit more clear. Like, I was not good at posting and sharing, so I set on my work calendar blocks that said you're going to go post something, right? And I held myself accountable to go do it. And it wasn't like 6 times a day; it was once a week for 3 months. Then it was twice a week, right? And then over time, I was doing it like now 6, 7, 8 times a day, right? It's just how that worked in. And again, I enjoyed it. I loved it. I found an avenue. I found the community that interacted with me, that participated, right? But having a voice externally, no matter how big or small it is always going to be valuable to you, whether it's a career in tech or a career in anything at this point, right? Having a social presence is becoming more and more important. And then if you find something that you're really interested in becoming an advocate for, right, that really is an accelerator, right, within that career path or industry, to kind of getting you more exposure. Yeah.